So our final speaker today is a name we're very familiar with. It's David Kelf, who's the CEO of Breker verification systems. He's going to be talking about automating checks through executable specifications and synthesis. Dave is a well-known EDA industry participant, having run Cadence's verification marketing, driven Synopsys verification strategy, and run marketing for Co-Design, who created the system Verilog. Novas, who had Verdi, and others. Today he serves as the CEO of Breker, the leader in test suite synthesis solutions. He has a solid engineering background, has performed many ASIC designs, and holds a microelectronics MSc from Brunel University. And he's based on the east coast of the US. So over to you. Thanks, Dave.
Okay, thank you, Mike. So in this presentation, what we want to do is talk about another way of automating verification checks, and that is using, indeed, actually the whole test bench, using the concept of test suite synthesis. So, we're all verification guys here, and we all know these charts, but the one in the bottom right I always find intriguing. This was a survey done by Siemens and Wilson Research, and one of the questions they asked is, what's the biggest verification challenge? And the big number that always comes up is just the ability to create sufficient tests to verify the design. And when you dissect that, getting the checks right, and indeed the coverage models, which I would argue is part of the checks, is a major part of that process. So the idea of automating this, or at least improving it in some way, is a very productive thought. So what kind of checks do we have to produce today? Well, if we're looking at the block UVM level, as some of the other speakers mentioned, you may use reference models, you might code up your own scoreboards, or find other different ways of incorporating checks in agents and different other mechanisms around a UVM test bench with System Verilog to basically build these checks. And however you do it, it still takes a lot of work and a lot of time, and it can be very error prone. And if we go up to the full SoC level, which is becoming more and more important these days, using real workloads with checks built in, essentially, comparisons with what we expect the results to be, or creating programmatic checks where we're testing parts of an SoC to make sure it's behaving correctly as we stimulate it, are all mechanisms that people use. And as I know Simon and the other folks mentioned, they all have their issues and problems, and something that we really want to try and improve in the best way we can. So what we want to try and do is look for new ways and new techniques to make it more easy to create these checks. So in dynamic methods, simulation, emulation, so on, we do what we know: send stimulus, write expected results, and check the coverage of tests. But thinking about what Yassine was mentioning earlier, using formal verification for some of this, it might be worth looking at other ways of creating checks and applying them to see if we can learn something from that. So with formal verification, we have this concept of a state map where essentially we look at the states in some manner like this, where states are on a vertical axis and the time and execution cycles are on the horizontal axis. So if we imagine the design is being clocked and the different states are changing as we move through that, some of the states are legal and can be used, the blue ones, and some may be red and illegal states, but all potentially can exist in the design in some way. So what a formal tool does, as we know, is essentially allows you to ask a question. So you can say, for example, does state Y happen after X, and what's the path between X and Y? And this is a very effective way of digging in and finding potential and difficult problems. The problem is, of course, you've got to create a data structure that holds all those states, and this is why formal can be difficult to use, and also it requires a huge amount of capacity. Although I would point out that what Yassine mentioned with these automated formal checks and what have you has come a long way to improve the state of formal verification and made it much, much more useful. So the question is, this idea of look at the check first and create the stimulus is a very interesting one, and one that it's worth seeing if we can learn from in the dynamic space. So can we do the same thing in dynamic verification? And I believe we can, and that's what we're going to talk about. So let's look at a simple test for testing the functionality of a car as an example. So let's say we start with the check in mind, where we think about what's the outcome that we expect. And in this very, very simple example, the outcome for this car is if it's not moving, we want it to go forwards. And if it is moving, we want it potentially to stop. So we start with that check and we say, well, what inputs do we need to control this car? And then, for example, if we want it to go forward, maybe we need the ignition switch to be on, the gears to be in drive, and the pedal, to be putting our foot on the gas, basically, or petrol, or accelerator, I should say, in Europe. So if we do this, we can, basically check, see if the car goes forwards, and we can check other permutations of those inputs to see if the car stops or doesn't go forward or behaves correctly as we expect. And we can do the same thing if the car is moving to see if we can stop it by essentially putting our foot on the brake. So this is a nice way of taking the check or the expected outcome first and looking at the different inputs to drive that. And once we've created this kind of high-level specification, what we can do is we can add to this with other scenarios. We could say, for example, let's start and stop the car 20 times and see if it overheats, for example. So this is a nice, straightforward way of building up essentially a specification. And as Simon mentioned, taking a specification that's executable or machine readable and seeing if we can generate tests from this. And this is essentially what we're doing with test suite synthesis. So the idea here, and by the way, this is a technique used by a number of portable stimulus tools, which is the way we describe the specification, either portable stimulus, this new Accelera standard, or we could also do it in C++ or use preset specifications that we'll talk about. So the idea here is that if we can take a synthesis technique, we can take all these input scenario models and basically synthesizing using coverage as a constraint, where we specify the coverage that we want to achieve, we generate tests, and these tests then at a generic level include both stimulus, but also include checks, coverage models, and even some debug information. So here now we're automating checks from this high-level specification, and we're trying to sort of create a more general check solution, which we can then map onto whichever verification platform we're targeting, be it UVM, block-based, SoC, or a range of other platforms as well. And why would we want to do this? Going back to that formal mechanism, what we're trying to do is start with the check. So if we look at, for example, what most constraint random tools would do today, which are, don't get me wrong, very useful and very effective, essentially what we're trying to do is constrain and drive a set of stimulus into a black box design to see if we can target the states that we need to go after and hit those states, and thereby performing a useful test. And that works very well for block-based designs and has a lot of power. But it very much depends on how you create those constraints and drive those tests. With this idea of test suite synthesis, what we want to do is start with the end in mind, start with those green states, and using that graph model, work our way backwards to the inputs. So essentially what we're doing is saying, we'll start with the state, we'll work our way back through the legal states to see if we can arrive at some inputs. And we use randomization and other techniques such as this to essentially end up at the inputs and produce a more directed form of test that can target these potential issues, all based on that specification model. So this is a mechanism for taking a readable spec and producing tests which essentially process that spec, and then we can drive those into UVM tests or SoC tests, depending on what we're doing. So let's look at some examples of actually doing this. And this is a very simple example, not much higher level than what you might do at UVM level, but this is an example of the UART. What we're doing here is configuring the UART, so the control structure goes from top to bottom with the configuration file, and then we're driving data into it, or both reading and writing the UART, and checking to see how this actually operates. And this is the horizontal direction, particularly sort of a UML type of diagram here. And you can see on the right-hand side that bit of portable stimulus code that's required to do this. And embedded within that portable stimulus code, we can just have these very straightforward high-level checks that are just simply comparing and making sure that the UART will be doing what we expect it to do. So if we run the synthesis technology on this, what happens is the first thing the tool does is flatten out that very high-level specification type graph into something like this, which is essentially the whole thing unrolled, randomized, and what we can do now is look and see how this test might actually operate. And you can see in various spots here, and if I can use my mouse, but at the lower right-hand corner of this, several checks actually implemented as part of this graph. And before we actually generate the tests, we can run some coverage analysis on this and get a sense, if we just let the synthesis tool go and do what it wants to do without too much coverage input, we can see areas that we can't hit, which are in red, areas that we hit a lot, which are dark green, and so on. So what we're doing now is we're looking to see where those checks are inside the graph and working our way backwards to that input. And we use this now to generate the tests for this UART. And we end up with something like this, where we have a number of tests, and basically on this flow, the green tests are ones that have already been executed on simulation in this case. The yellow tests are ones that are in process, and the blue ones are yet to be simulated. And that little red spot in the middle is a test where the automated check inside it has failed, and you can actually see on the screen here where the failure is and what's going on. So the idea here is that we process, if I go back to this, we go from the right-hand side to the left-hand side, we generate tests, and then we actually schedule multiple streams of these tests all together to see if we can fully ring out the coverage and find any issues that may be existing inside this design. And the nice idea is that we're taking the specification and we're really digging in and figuring out some very potentially nasty corner cases that are hard to predict in advance. If we look at a bigger version, this is a cache coherency graph. It's actually just the high level of it. Underneath each one of those nodes is another sort of bigger, more elaborate test. And interesting that Simon picked RISC-V. This is also RISC-V cache coherency test. The idea here is that we can, inside this graph, as we did with that car example, we can embed simple tests. And at this level, all we need to do is do memory checks to make sure the memory is consistent, since we're doing cache coherency here. And the different levels of cache, together with the rest of the system, is all consistent with each other as we go through and run all these different algorithms. And the kind of tests that this would generate looks something like this, where essentially we have multiple threads, software threads, running and executing these tests. And again, you can see we can run through this, and if a check fails, i.e. a memory comparison is incorrect in some place, the test can simply turn red, and you can go and figure out what's going on. So by starting with this executable specification and automating the tests built into the test bench, we can quickly see what is actually happening inside the design. A little bit annotation there. And of course, as you see mentioned, this idea of providing automated encapsulated tests in formal verification can also be brought into this kind of environment as well. So what we're able to do with these graph-based tests, including the checks, is basically encapsulate them in system VIP type libraries, we call them TREC apps, to do various functions here. And so what we're able to do is provide one of these, configure it for the particular design situation, the processor, whatever it is, and execute these tests. And the checks are included inside it, and they just run and fire if they find difficult corner cases. So to summarize then, we know that test content composition is a tough verification challenges, and the checks and providing coverage models is one of the most difficult parts of that. So it's worth focusing and seeing if we can improve this. I don't believe there's any silver bullet, honestly. Formal verification has come a long way, where you can ask questions and get answers about the design. But I think if we can simplify the creation of checks and coverage models, and we can do this at an abstract level, this can lead to a lot of potential, a lot of power. And we can do this through the use of synthesis, essentially. And we have seen this in action at some pretty large companies who are doing a lot of SOC testing as well as UVM, and testing things like cache coherency. And we can see the kinds of improvements that we get, a big reduction in the amount of manual effort to create these tests, as well as increasing coverage. And that's my presentation, Mike.
Thanks, Dave. Thank you very much. Very interesting. So you seem to be suggesting that we sort of do check or coverage-driven test generations, so moving from right to left, correct?
Yeah, that's right. Yeah, so you start with the check on the right, and then you work your way backwards through the graph. That allows you to produce the test, which are then applied to the design, of course. So by using this readable spec and finding a way to process the spec, this allows us to really produce some very comprehensive, powerful tests and embed the checks inside it at this higher abstract level. So it produces a lot of power and makes it much simpler to do.
Okay, and one of the things this suggests or promotes would be to use some level of AI or ML to improve that test generation process.
That's correct. Yeah, thank you for mentioning that. I probably should have said it myself. So the way we backtrack through the specification is we use a technique called planning algorithms, which is actually pioneered by IBM. And IBM has publicly said they're a customer of Breker, and they use these planning algorithms techniques in their verification. And the idea is that together with randomization, we can make more intelligent random decisions, backtracking through that design to find the most efficient tests that will then target those checks. So it does indeed use an AI technique, planning algorithms, and we're improving that all the time and looking for other ways of making that more efficient.
Okay. One question online as well is that the questioner suggests that sometimes illegal scenarios may be useful to generate to try and break the design. Yes. Do you have any comments about that?
Absolutely. In fact, so the question is absolutely correct. And in fact, it's an essential part of creating these tests. The scenarios we can create, of course, you can create legal scenarios and say, this is how it should be working, but you can also create the negative of that, right? You can say, this is a test. I want to make sure, X does not happen in this situation. Or I want to make sure that the tests that are generated not only go through those legal states in that state diagram, but actually can work their way through the illegal states as well, and see if they can put the design into some kind of strange state that that can cause trouble and find extra corner cases. So that's definitely part of this, and it can definitely be coded in very easily.
Okay, thank you very much, Dave. Appreciate that. Thank you.
Appreciate it.
Thank you, Dave.